In this video, we're going to work an example of curve sketching, which is just really drawing the graph of a function, but drawing it manually without the use of some graphing utility. Although if you're practicing curve sketching, you should definitely use a graphing calculator, and there's a bunch of great free online tools such as Desmos or GeoGebra or GraphSketch, and I think some of these are available as an app now as well, so check those out. If you're taking a course in calculus, then curve sketching is almost certainly going to be on the curriculum. Curve sketching is a core calculus skill, and the great thing about curve sketching, it requires the pulling together of a bunch of different calculus skills. So if you're doing curve sketching, you're doing it well, that is validation that your calculus skills are up to speed. Also, it's just likely that if you're taking a course in calculus, you're going to be tested on curve sketching at some point, so it's going to appear on assessments. Curve sketching is important because it allows us to visualize the behavior of a function. So when you see a function in its algebraic form, like this here, you don't immediately know very much about that function. You might know a couple of things, but if we can get to the point where, as we're going to do in a moment, sketch the graph of that function, then we can immediately start to see some of the behavior of the function, like where is the function increasing or decreasing, where has it got its key points, like the maximum and the minimum points. Just stuff like that allows you to get a visualization of the function, which can be more powerful than just seeing the function in its algebraic form. So how do we go about actually sketching the graph of a function? Well, mainly, if you imagine we've got an xy axis, we need to know where to put our function on that xy axis, and we're going to sort of anchor the function by its key points. And the key points really are the x-intercepts or the roots, the y-intercept, and the turning points or the stationary points, the local maxima and minima of the function. Now every function obviously is different. This looks like a quadratic function, but if you remember that the x squared is going to multiply to the x term in the bracket, then that would actually become an x cubed. So this is actually a cubic function. So it would be useful to know already before you sketch it the general shape of a cubic function. So cubic functions either go basically this way, like this, and they carry on forever, or they can go down this way. And this one is where the x cubed term is positive, this one is where the x cubed term is negative. If we multiplied out this bracket, which we're going to do in a moment, the x cubed term will be negative. So by knowing that general shape, and that's just something that you need to ideally know, you know already your graph is going to look a little bit like this. But you don't need to know that general shape really, because if you find the key points, then you can just fill in the shape between those key points. So that's really what we're doing in curve sketching. We're not plotting point by point. That's not really curve sketching. This is curve sketching. It's just a sketch. It's not a perfect diagram. If you want a perfect diagram, you need to plot point by point. You need to basically use some kind of graphing utility. We're just trying to get an accurate sketch, but it is still just a sketch. So we reckon we're probably aiming for something that looks like this. So let me just start by multiplying out these brackets, and then we're going to chat more about what we're going to need to achieve our sketch. So x squared times 2 gives us 2x squared, x squared times x gives us x cubed. So that just puts it in a form that we can do more stuff with than the bracket. So every function will be different. You might not have a bracket in the functions that you work with. Sometimes you will, sometimes you won't. So what do we need? Well, there's a few things that we need. We need to know the things I mentioned a moment ago. So we're going to want to know the x-intercept for our particular function, where it cuts over the x-axis, and there might be multiple places where it does that. We're going to want to know the y-intercept. There can only be one y-intercept for a function, so there should only be one of those. If we get more than one of those, then something's gone wrong. And it depends on how complex a function is as to what else we need, but we certainly need the stationary points. Or you might call those the local maxima or minima points. So stationary points, basically the turning points, where the graph of the function changes direction. Because if you know those points, then that's just going to help you to fill in that shape. If this was a more complex function, we might include some additional things here, for example, asymptote lines, which are really important in certain function types. I might make another video on that at some point with a more complex example. That's for things like discontinuous functions, where you've got a discontinuity somewhere in the graph. The graph basically jumps over the asymptote line, but we don't need to worry about that for this particular example. This is a continuous function because it's a polynomial function. Okay, so it doesn't really matter the order in which you get these things. You're going to need all of them, and then we're going to piece them together. So we're going to start by working up these. Once we've worked these up, we're then going to try and plot some of these key points over here. And these are really just about getting the key points. We'll mark them on our XY axis, and then it should be trivial to just fit in the shape. And we're hoping that the shape comes out to look like this, because that's our prediction for this particular type of function. It's really, really useful to learn the general shapes of a few different common function types, like x squared functions, parabolas, x cubed functions, x to the power of 4 functions. Then you can just sort of self-check or validate that your answer actually makes sense. So I think I'm going to start with a stationary point. So the stationary points, finding stationary points is a core calculus technique. To achieve that, we need to take the derivative. How you take the derivative will depend on the function. In this case, we can use the power rule. Hopefully you're already familiar with taking derivative and indeed with finding stationary points. If not, you really need to get good at these core skills before you can do curve sketching. Or you could say that you're going to learn those skills as part of curve sketching. So if you're not sure about these, just follow along and try and pick up these skills. I've also got some other videos on the stationary points, and these two tend to be easy enough, so you should pick those up if you're not familiar. But ideally, before you come to curve sketching, you would have some experience of all of these. So let's start with the stationary points. For the stationary points, we take our derivative. We can take the derivative here using the power rule. So the 2x squared differentiates to 4x. The negative x cubed term becomes a minus 3x squared. And then it's good to write in a little sentence, something like, for the stationary points, or for the local maxima or minima. I'm just going to abbreviate that to for SP, stationary point. The derivative has to be 0. The derivative is 0 always at the stationary point. So this is the sort of key fact we're going to use to help us find those stationary points. So we're just going to take that derivative, which is now 4x minus 3x squared, and we're going to set it equal to 0. And it's good just to put in this line of work in here, just to tell the reader, probably your teacher or whoever's checking your work, why you're setting it equal to 0. A lot of the time this will be mandatory in the working. So we've set it equal to 0. Now we need to solve this equation. This is a quadratic equation. We're going to have to solve it by factorizing. So I'm going to factorize by pulling out a common factor. It could be that this is some different form. Whatever form you get, you're just going to have to work with it and solve the equation. A lot of them do come out to be quite easily factorizable. So we're going to get x outside the bracket. X is a common factor, and then we're going to need 4 minus 3x inside the bracket, keeping that equal to 0. Separating these off into two mini equations, I guess. You're going to get x equals 0, so x equals 0. And then inside of the bracket, 4 minus 3x equals 0. This one's already solved, x equals 0, so that's fine. The second one we can solve just by, well, it's a linear equation, just by moving some of the terms around, and you would find that comes out to be x equals 4 over 3. So these are the x coordinates of our stationary point. So we could already start to kind of work out what our graph's going to look like a little, but we're going to need really the y coordinates to go with these. To find the y coordinates, we're going to have to substitute these back into the original equation, either this one or this one. Probably this one's easier, maybe, and work out the y coordinates. The x0 is going to be easy, because if you put 0 in here and here for x, you're just going to get y equals 0. So that one's a bit of a no-brainer, and that quite often is the case. If you get a 0, the other one will be 0, not always. So those two form a coordinate, the coordinate 0, 0. The next one, 4 over 3, it's quite an awkward number. Ideally, we would prefer these to come out to be nice whole numbers, but we're just doing the same thing. We're subbing it back in here to get the y coordinates. Let me just go ahead and do that. I'm just going to do it up here. So we're going to be doing 2 times 4 over 3 squared. You might be able to use a calculator for this in some classes, but on an assessment, don't be surprised if you've got to do this manually. It's a bit of a pain, it's a bit of numeracy, it's quite annoying to be honest, but you just got to sort of churn it out. Okay, so let's check this out. 4 to the power of 2 is 4 squared is 16. 16 times 2 is 32, and that's going to be over 3 squared, which is 9. Here we've got 4 cubed, which is 64, over 3 to the power of 3, 3 cubed, which is 27. We want to tidy this up a little, so we can make that first fraction into 27ths as well by multiplying top and bottom by 3. So it's going to become 96 over 27. I admit that I never practiced this question ahead of time, so please do check my numeracy. So 96 minus 64 over 27. You might think at this stage, wow, why is this becoming so numerical? This is just the way it is sometimes. Sometimes you'll get really nice numbers here. If this had come out to be like a 1 or a 2, that would be awesome. It's just that in reality, it's not always like that. So it's good to suck it up and face the pain and try a few with these awkward numbers. This would simplify to 32 over 27. So that tells us the y coordinate that goes with x equals 4 over 3 is 32 over 27. So what are these? These are our stationary points. So we've got one stationary point at 0, 0. We've got a second stationary point at 4 over 3, 32 over 27. Now, when it comes to sketching our graph and plotting these points, 0, 0 obviously is a no-brainer. We don't need these to be quite this accurate. 4 over 3 is pretty close to 1. It's 1 1/3. We can sketch that on just a little bit beyond 1. 32 divided by 27 is pretty close to 1 as well. It's just a little more than 1. So this coordinate is actually 1 1/3 and something a little bit more than 1. So it's almost 1, 1. So that just gives us a good enough estimate to plot those onto the graph later on. Okay, cool. So that is our stationary points almost done, but we need to know the nature of these stationary points. What type of stationary point are they? Are they a local maximum, minimum, or point of inflection? So it's not good enough just to get the numbers. We need to know the shape as well. I suspect the graph looks like this. So I think that first one will be a minimum and the second one will be a maximum. That 0, 0 is probably this one, a minimum, and the second one, which is further to the right, this one here, should be a maximum. So that's the expectation. And knowing again, this here is really useful because it can help validate the next part of the working. The next part of the working is to, well, there's a couple of ways you can validate the nature of these stationary points. I'm going to use a nature table. You can also use a second derivative. So setting up your nature table, whichever of those methods you're familiar with is fine. Putting in the x coordinates of your stationary points, but remembering to leave enough space for other numbers as well. So we need 0 and we need 4 over 3. These need to go in numerical order, going left to right. Choosing numbers to the left and to the right of these points, I'm going to go with minus 10 here, and I'm going to go with 1 here, and I'm going to go with 10 here. These are your choices. Just make sure they fit into the right place. You know, this has to be a number bigger than 4 over 3. This has to be a number between the two stationary points, and this needs to be smaller. You can choose any numbers, but don't choose stupid numbers. There's no point in making this a 7. Why? Because 7s are horrible numbers to work with. 5s are good, 1s are good, 10s are great. 10s are my favorite because they're super easy to calculate with. As long as you don't go past the next stationary point, you're good, but there are no more stationary points. So I could choose 100 here if I want. It's not going to cross over another stationary point, so it's in the right place. Okay, so also in this table, we need our derivative, and then whatever you want to call the third row, like the shape or the slope or something like that. It is kind of the shape because it represents a mini sketch of the graph. So that's the great thing about nature table as opposed to using second derivative. Once you've completed your nature table, you've got like a little stick diagram of the graph. It's really powerful for this type of question. Much better, I personally think, than using second derivative. Second derivative will tell you the nature of the stationary points, but in a less useful, personally, I think, way. So underneath your stationary point, 0 and 4 over 3, you can just put in a 0 in the derivative row because we know the derivative is 0 at those points. Now we need to know whether these are positive or negative. We don't need the actual numbers just to know whether they're positive or negative. Negative 10, remember we're subbing this into our derivative, which is here. Negative 10 times 4 is negative 40, but negative 10 squared is positive 100, times minus 3 is minus 300, so 40 minus 300 is negative, which is what we thought it would be, because this part of the slope here, the graph here, is got a negative slope. 4 times 1 is 4, minus 3 times 1 squared is 3, so 4 minus 3 is 1, which is positive. So that tells us between the stationary points, the graph should be going up because of the positive slope, which we can see again on this one it is. And then finally 10, well 10 gives you the great thing about using minus 10 and 10 is if you have to square, if you've got an x squared term, minus 10 and positive 10 squared are both 100. So we're going to get the same result actually for the positive 10 here. It's going to be negative. You can check my working if you're not quite sure, but you can see that beyond that second stationary point over here, the graph is sloping down. So that should have a negative slope. So remember, the derivative represents the slope. If the derivative is positive at a particular point, the graph is sloping up the way. If it's negative, it's sloping down the way. If it's the turning point, then it's got zero slope. These are the turning points, the stationary points. So that tells us then that in this part of the graph here, to the left of the first stationary point, the graph is sloping down the way. Then it goes to 0. We represent this by a little line, but remember, in reality, that's not a line. It's not a flat part of the graph. It's just one single point. Then it goes back to positive, then it goes to 0 again at the next stationary point, and then it goes back to negative. And in this part here and this part here, these actually carry on, remember, forever. Okay, so that definitely deals with stationary points. Let's move on and have a look at the y-intercept. So the y-intercept is really easy because for your y-intercept, you just let x be 0. Because if you think about it, if you're a point on the y-axis, your x-coordinate has to be 0 because you're on the y-axis. So let me actually just, well, we'll work that up in a moment. You'll see how that pans out in a moment. But we're just going to let our x be 0. In fact, to find the y-intercept, you let x be 0, and to find the x-intercept, you let y be 0. So you just let the opposite letter be 0. So going back to the original function, be careful not to plug this into the derivative. You've got to be careful with that. Letting x be 0 in the original, 0 minus 0 is 0. So that tells us that the y-intercept occurs where y is 0. So the full coordinate there is 0, 0. Now that's the same point we had earlier. So that y-intercept point happens to also be a stationary point in this example. That's not always going to happen. Sometimes it will, sometimes it won't, but there's nothing wrong with that. That's perfectly fine. Finally, so we can tick that one off. Finally, getting our x-intercept. So for the x-intercept, we're just going to let y be 0. This one tends to be a little bit more difficult because with this one, you're just subbing in 0 for all the x's, which tends to just wipe out a bunch of terms. When you're letting y be 0, you're putting the 0 on the left-hand side, which is giving you a little equation to solve. So we now need to solve this equation. We're going to have to do that by factorizing. We can do that by pulling out a common factor. I'm just going to switch my 0 over to the other side actually. So pulling out a common factor here of x squared, and then we get 2 minus x, is that right? Yep, equals 0. Solving that, we're going to get x squared equals 0 to give us x equals 0. And then we're going to get 2 minus x equals 0 to give us x equals 2. So what does that tell us? Well, again, we've picked up the point there, 0, 0. So I'm not even going to bother writing that one down because we already knew that that point is both the x and the y-intercept because it's right on the origin, it's 0, 0. But we have picked up some additional information here, which is the point 2, 0. Make sure you get the order, the x and the y order correct. So it's 2, 0, not 0, 2. So we've got everything we need now. We've got our x-intercept, or intercepts, and remember that these are also called the roots. We've got our y-intercept, we've only got one of those, which is good. We can only have one of those, and then we've got our stationary points. So basically these key points, let me just highlight them in red. So 0, 0, this guy here, and then this guy here, these are all the points that we need to plot the points and then to sketch in the graph. We already know the shape of the graph. So this is the critical moment. When you pull all this information together, it should all be consistent and you should get a graph that looks like the thing that you expect it to look like. If you don't, if something is out of place, if some of the information is not consistent, then it just means that something's gone wrong. It might only be one thing that's gone wrong and you just go back and you check for it. and you find the inconsistency, and then it alerts you to the fact that something's gone wrong. So we know that the point 0, 0 is on our graph, so we can put that point there. We also know that that point is a minimum turning point, so that's at the bottom. Remember, in reality, this is going to be a curve, so this is going to curve like this. Not obviously it's not just going to be like straight lines, like a stick diagram. So we expect our graph to come down here and turn on that point. Let's fit in some other points. So this was the guy 1 1/3 and then roughly 1. So let's say that 1 is like there, and then 2, and then 3, and we'll just go back the way as well, like -1, -2, -3. So 1 1/3, a little bit past 1, and let's actually just put a couple on here as well. So let's go 1, 2, 3, and we'll just go 1, 2, and 3, or -1, -2, -3. So this guy here, just a little bit past 1, so 1 1/3. 32 over 27 is a little beyond 1, so that point is going to be roughly up there somewhere. It's not perfect, it's just a sketch, doesn't have to be exactly in the right place, but that looks pretty consistent because we expected it to come down here and turn, which would allow it to go up there. That point, remember, is the second turning point where we expect it to turn back down, so this is a minimum turning point, local minimum. This is a maximum turning point, or local maximum, so that's consistent so far, so it's all looking pretty good. This point, remember, was a intercept. This is the point at 2, 0, so 2 along, 0 up, so that's the point there. So maximum, minimum, intercept, graph going like this. Does it all fit together? Yeah, it looks pretty good because the graph should be sloping down to that first turning point, which is this guy here, then turning back up, then turning back down and intercepting here. If this intercept point had ended up, say, back here, there's no way the graph can go up there, do that, and then come back the way. Graphs don't work like that, so it all fits in pretty well. So you can just sketch it roughly in like this. I hate when I sketch the graph and I miss the points and it all comes out wrong, but I managed to get the points, so it looks pretty good. Remember, in reality, the graphs carry on forever, so this guy, or this type of graph carries on forever anyway, so this would actually continue all the way up here and all the way down here. But again, this highlights the point of graph sketching, right? This graph is just going to carry on up the way forever here, down the way here. So this part here is not very interesting, it's just going up. This part here is not very interesting, it's just going down. All of the action is happening around here. That's why we focused on finding these points. We could have found a point like randomly, some point over here. It's just that there's nothing happening over there. We want to know where it's crossing the x-axis, the y-axis, and where it's got its turning points. That's all the key information about the behavior of that function. So that's really one of the key reasons why we do curve sketching. So that's just one example of curve sketching for a relatively straightforward function. You can get significantly more complex functions, and I might have a go at some of those in a video in the future. But hopefully that gives you a flavor for how curve sketching generally goes. It's definitely a core, key, really useful skill to practice if you're taking a calculus course, and one that you're almost certainly going to be tested on. I think it's something that needs quite a bit of practice, so don't just learn the theory, don't just learn the steps, but have a go at quite a few of these and try to mix up the function type as much as you can, and you'll start to learn to look for the shape. Notice how my prediction here, which I got from really just the original function, came out pretty close to the actual thing. Now that's because I'm a nerd and I do these all the time, right? But just by a little bit of practice, you'll be able to do the same thing. So I hope that helps. Any questions or comments, please just leave them in the box below.